Now today we will discuss about the design of a structure, of course, that we will summarize in this episode. Whenever bending is occurring, suppose in a beam or in a slab, so whatever bending strength of that given grade of concrete is there, it should be more than the load coming on this structure. Bending strength should be more than the load. Of course, strength will be taken in ton per meter square and load in ton. So far as this column is concerned, upward pressure is acting. That is, whenever beam is resting over the column, load is coming from both sides of the slab over the beam, and this load is coming on the column through the beam. So there must be some reactive component, of course. So the upward pressure is acting in the column. That's why for column design, that is cross-sectional area for column, that direct stress will be taken into consideration. When we will take the direct stress into consideration, that sigma Cc, which is permissible compressive stress for that given grade of concrete. Suppose in a pier, 1056 ton load is acting on the pier. So of course when we will take M30 grade concrete, its sigma Cc is only 8 Newton per millimeter square, which is 800 ton per meter square, which is less than the load, that 1056. That's why we will take more grade of concrete, of course M30 35, or that more than M30, M35, M40, whatever is there, that permissible compressive stress, that strength should be more than the load, of course. Sigma Cc should be more than the load coming on the pier. So we will design the cross-sectional area of the column with respect to this sigma Cc. P by A should be equated to sigma Cc. We can find out the cross-sectional area of the column. Now of course, whenever load is acting, vertical load on the column, the lateral load can be given by 1 minus sine phi by 1 plus sine phi into vertical load. Phi is taken as 35 degree for concrete. So we can find out this lateral load which is acting on the height of the column and width of the column. Now we can find out the load intensity, of course, if height of the column and width of the column are comparable to each other. Suppose 1 meter is width, suppose, and height is 4 meter, 5 meter, like that. We can take lateral load. These dimensions are comparable to each other. Load intensity can be given as lateral load divided by this surface area, of course, that height of the column and width of the column. That will give you the load intensity. If height of the column is more than the width of the column, suppose only 400 or 500 millimeter width, height is 8 meter, so it is the case for transverse load, because width is very small. That is, in case of beam, length is very much more as compared to width on which load is acting, load bearing area. So that is termed as the transverse load. In that case, lateral load divided by only height of the column that we will take, that is transverse load, when width is very small. That's in this way that load intensity can be found, and height of the column is bending. We can find out the bending moment, that is WL square by 8. And using bending equation, we can find out the depth of the column. In this way, the cross-sectional area of the column can be found against bending. Or that is bending, not buckling, that is axial compressive load is there on column. So here, that in this way, that with respect to direct stress and bending stress we have found. Now there is a check how you will find this appropriate cross section of the column. P by A divided by sigma Cc plus P into E by Z by sigma Cbc should be less than 1. Eccentricity we can take height of the column divided by 500. In this way, that the cross-sectional area of the column can be fixed. So, this is the, now in case of beam as well as this column, this bending is occurring, of course, no upward pressure is acting, that's why it will be designed against bending. That we will use M by Z is equal to F, but in column we will use the direct stress as well as bending stress both. Now, suppose reinforcement we are using, of course. Now we can take the reinforcement for column 1% of the cross-sectional area. We can find out the longitudinal reinforcement, of course, that much number of bars. Amount of reinforcement can be found 1% of cross-sectional area divided by area of 1 bar, that is 16 mm or 20 mm bar. We are taking dia pi by 4 d square, that is A5 will be pi by 4 d square. You can divide this AST by A5, we can get the number of bars. In case of beam, we can use 0.6% of cross-sectional area, 0.7%, and for slab we can take 0.6% of cross-sectional area, that is B is taken as 1000 mm, and whatever depth of the slab is there, we can take that one. So in this way, that amount of reinforcement is known to you, so that's why divided by area of 1 bar, we can find out the number of bars. And a spacing for column can be found by 1000 A5 by AST. AST amount of reinforcement which can be found by 0.6% of cross-sectional area. So this is about the main reinforcement. Of course, for slab we can use this distribution reinforcement 0.15% of cross-sectional area. And spacing 1000 A5 by AST, we can find out the spacing. Now, so far as shear reinforcement is concerned, now of course in column also we can provide ties, so that spacing should be 48 dia of 5, that dia of this tie member 6 mm we can take, and we can find out the spacing. Or 16 phi, that is of main reinforcement, that when we dia of that main reinforcement, that is 16 times of that, or least lateral dimension, which one will be the least among these, we can find out the spacing for ties member. Now of course, so far as this is acting like shear reinforcement. Why that? Because Shear, that is vertical force. Of course, whatever load is acting, that is shear force, of course, because summation shear force, that is summation of vertical forces about a given section. We can term that this one is shear force. So it is related to vertical force. So far as the beam is concerned, we can provide the shear enforcement in terms of stirrups, of course. Now, so far as the vertical load is there, there must be deflection, of course. So this shear reinforcement has the role to take the vertical force, whatever it is coming. That's why it is called shear reinforcement. It neutralizes the bending, of course. This is the role, of course. Whatever deflection is produced by vertical load, this neutralizes the bending. This is the shear reinforcement, of course, that can be used in terms of stirrups. Now, at the this reinforcement, this support, it should be closer spacing should be provided, and in the mid span, more spacing we can take that 150 mm center to center we can take, but at support 125 mm center to center. Now why? At the support, see here, at the support shear force is maximum, of course. So that's why shear failure, for shear failure we can take this type of thing, that shear reinforcement should be, spacing should be closer to each other, that near the support, of course. Now, of course, from the support Ly7 distance, whatever span of beam is there, Ly7 of that, we can bend the bar, and that is at 45 degree near the support to take the shear. Now, when we will not take in bent bar near the support, suppose somebody says that we will take a straight bar. Now, of course, whatever shear force at the support, that is WL/2, suppose UDL is there, so reactive component will be WL/2, of course, at the support. That is, the force is acting at the support. So, of course, this we can find out when it is in bent form. It will that it first it tries, due to the load acting the support, it is maximum. It tries to be straight. It will take that much amount of load. That's why we use this bent form for shear reinforcement near the support. Now, of course, this we can find out when we will take that straight, not it is in bent form. So, of course, shear stress produced by load we can find out. That is load, whatever that load is acting at the support, divided by cross-sectional area of the bar, which can be pi/4 d square. That will give you the shear stress at the support. So, load divided by pi/4 d square, suppose 20 mm 5R, you are using pi/4 d square. So, this is shear stress produced by load in that reinforcement, of course. Now, we will see for concrete also. So, this reinforcement, that whatever load produced by this shear stress produced by load, it will be more than the shear stress by this shear strength of this reinforcement, which is 0.3 Fy, characteristic strength of that given grade of steel. Suppose Fe 250, so 0.3 of 250 So that load produced by this shear stress produced by this load, if it is more, suppose when we are taking in a straight form, so that will be the more than the shear stress by the shear strength by further reinforcement. So we will not take in a straight form, we will bend. Okay, so whatever load is acting at the support, that load divided by 2 bar, suppose 2 bar we are bending, so 2 into pi by 4 d square, suppose 20 mm 5, so that will give you the shear stress due to load. So that shear stress due to load, that is shear, it is satisfying 0.3 Fy, which is shear strength of steel. Then we can say it is safe. So we will bend the bar near the support, that is shear. Now what will happen, that is why shear stress check is to be done. If that load produced, the shear stress produced by load, if it is more than the shear strength of concrete or steel, shear failure will take place. That is, shear means tangential action, that is sliding will occur in internal part and cracks will develop and failure will take place due to this shear. That's why it should be checked against shear. Okay. So for concrete also, that near the support, suppose whatever WL by 2 you can find out the load divided by whatever width of the beam is there and depth of the beam. So load divided by that area B by BD, we can get the shear stress produced by load. So this should be checked with shear strength of that given grade of concrete. So that load produced by shear stress should be less than the shear strength of concrete. So for concrete also and this reinforcement also, we have to check. In slab, every third bar will be bent, that is main bar, at near the support, that is at Ly5 distance from the support. So in this way, that is for shear, this is shear. So actually these are the two parameters for design of a structure: bending moment and shear force, of course. From bending moment, we can, whenever bending will occur, we will use the bending equation to find out the thickness of that structure, and this thickness will be deflection can be found, that thickness is appropriate or not. It should be checked with the deflection. Delta can be FL square by 6 ED in case of concentrated load, and delta is equal to 5 by 24 FL square by ED. F is fractural strength, of course. L is a span, E is modulus of elasticity, and D is the whatever depth you have found by using bending equation, you can find out this delta. So this should be compared with this permissible value, that is a span by 350 for beam, suppose, or slab, that is bending is occurring along the shorter span, that span will be taken. So in this way, that bending moment as well as the shear force, that is load produced, that is shear stress produced by load, it should be checked with the shear strength of concrete as well as shear strength of reinforcement, of course. These are the two things for bending so far as bending is concerned. Now suppose whatever the structure, it is made on ground like pavement, road, of course whatever material you are using, suppose aggregate, stone dust, this boulder, etc., its strength, compressive strength, remember that whatever load is acting due to the vehicle, that load should be less than its compressive strength, okay, for that given material. In bending, that bending strength should be more than the load. This is the difference. That is, whenever bending is occurring and whenever this compressive, that upward pressure is acting due to swell, that is below that swell pressure is there, upward pressure is acting. In that case, we will take compressive strength of that aggregate, suppose in road, its compressive strength should be more than the load coming from top. So first we have to see this thing. Now, in case of bending, that is, we will check against deflection. Similarly, here, whatever structure is made on the ground surface, it should be checked with settlement parameter. Remember that, this thing, settlement parameter. Now, suppose in rainy season, what will happen? That penetration of water will take place. Suppose water logging is 2 meter or 3 meter on the road. So, depth of soil, that is penetration of water will take place 0.6 of that depth of water logging. That much penetration of water will take into soil. So that much soil will be in moist condition or saturated condition, of course. Now it will be in muddy condition also, that is in flood case, suppose flood is there. Or continued water logging is there, it will be in mud condition. So total strength will be lost of the soil. Because muddy soil has only phi, that is phi is 0, and that unit weight, that is 1 ton per meter cube, of course, only. So it has no strength, of course, muddy soil, okay, if it is very saturated. So whole that, suppose 20 ton per meter square, for that we are designing this soil, whatever. Totally lost, 20 ton per meter square is lost due to mud form. So we have to provide extra foundation, more foundation, for that this much reduction in bearing capacity. That is, depth of foundation can be found as 20 ton per meter square divided by below this penetration of water below the dry soil is there, which gamma is 1.85, phi is 30 degree, 1 minus sin phi by 1 plus sin phi whole square. Df is equal to 20 ton per meter square by gamma into 1 minus sin phi by 1 plus sin phi. Phi is 30 degree. We can find out the more depth required for this much lost when it is muddy form. Similarly, in this pier design, that is in bridge also, penetration that will take place, of course, for whatever loss in bearing capacity, we have to provide the more depth of foundation. So that much depth of foundation we have to provide for that much reduction in bearing capacity. Whenever it is in moist condition, when it is in saturated, in moist condition 25% bearing capacity is lost. In saturated condition 50% of bearing capacity is lost. In muddy form, total strength is lost. So for that much length, that much depth, we can find out the settlement. Settlement will be that much loss, that is 20 ton per meter square is lost, and that much depth on which the water penetration takes place, that depth multiplied by the soil properties, that is depends upon the void. So that we can take 3.62 or 7.62 into 10 to the power minus 2, we can find out the settlement. Of course, for clay soil it should not be more than 40 mm, for sandy soil, for clay soil it should not be more than 65 mm, and for sandy soil not greater than 40 mm. So in this way settlement can be found. Now whatever reduction in bearing capacity takes place, for that reduction we have to provide more depth of foundation. Now coming to the is covering of soil, of course. Now, of course, suppose in a pier, suppose height is 14-meter depth of water from bed of the river. So uplift pressure will be acting, which magnitude is W into H. Of course, we can find out W is unit weight of this water. So we can find out the thrust. Of course, there will be some whatever velocity we can take in flood case 1.2d. That is whatever depth we are taking, that is V can be taken, the V can be found 1.2d, and thrust due to velocity, that is WVS square by twice G. So due to a standing water, that is as well as velocity, we can find out the total thrust actually, that is uplift pressure. Now it is advisable for bridge that it's always, which is in river, it should be constructed on the rocky strata. Remember that, not on soil. If it is made on the bed of soil, covering will take place and the failure of the bridge will take place. That's why it should be made on the rocky strata, of course. Okay, so here pier, so far as pier is there, so we can, of course, that will be in submerged condition rock. Its strength is very much less than the lost, that is when it is in submerged, that is below the foundation base. So it can take the uplift pressure that rocky strata, no failure will take place. If it is in soil strata, that it is due to uplift pressure, that is covering will take place and failure of the bridge will take place. So it is must, that is it should be checked with the settlement, whatever the upward soil pressure is acting for the structure which is made on the ground, it should be checked with settlement parameter. Remember that. For road also, that if it is in muddy form, so total loss of bearing capacity is there. For 20 ton per meter square is lost for that much depth of muddy soil. So for that, we can find out for 20 ton per meter square, that is more depth of foundation should be provided. So suppose DF we can find out, that is 20 ton per meter square is lost, divided by gamma. Below that soil, saturated muddy soil, we can provide the more depth of foundation, which gamma can be taken as 1.85. Phi is 30 degree. So according to that, DF can be provided more depth of foundation. So far as, of course, here also, due to penetration of water seeping into the ground, uplift pressure will be acting. So we have to take the covering problem also. So in the submerged bearing capacity, suppose 50% is lost. So 10 ton per meter square is there bearing capacity of the soil below the muddy soil. 10 ton per meter square, but uplift pressure is supposed 2 to 3 ton per meter square. It will not cover the soil below the muddy soil, that is which is more depth of foundation below the muddy soil we will provide. So is covering parameter as well as settlement parameter, these are the two things should be taken into consideration for the structure which is made on the ground where upward soil pressure is acting. Okay, thank you.